Good morning, everyone. This is Dhanalakshmi, Assistant Professor from Tripoli Department of RMD Engineering College. In this session, I would like to discuss about signal flow graph. In short, we will call it as SFG. This is actually the significant part of our control systems. As we know that in control systems, our unit 1 is all about deriving the transfer function of the given system. So in that, the signal flow graph is a very important, significant methodology to obtain the transfer function. So we have another methods also, other techniques like a block diagram reduction. So many techniques we have. So in that, the signal flow graph is a significant one. So let me discuss signal flow graph in this session. Okay. So signal flow graph, in short, we will call it as SFG. So the signal flow graph tells you the flow of signals from one node to another node, that is from the input point to the output point. So like block diagram reduction technique where we will be getting a transfer function, the same way in the signal flow graph also, using signal flow graph, we are going to obtain the transfer function of the given system. So we know already that the transfer function is the Laplace transform of output by Laplace transform of input, assuming all initial conditions to be 0. So so before proceeding with signal flow graph, and where the objective of the signal flow graph is to obtain the transfer function, first we should know about the Mason's gain formula. So Mason's gain formula, it states as that it gives you the transfer function T of S, which is actually the Laplace transform of output by Laplace transform of input, that is C of S by R of S. The formula for this transfer function by Mason's will be 1 by del summation of k pk into del k, right? Where this pk, where this k stands for the number of forward path. So in a signal flow graph, first the foremost step is to find the number of forward path. Then the number of forward path will be k, and based on the k, we will be getting the path gains. So therefore, after finding the number of forward path, we have to find out what is the path gain of the kth forward path. For each and every forward path, we have to find out the gain. So that is going to be my pk. Then we have to find out the del value. So here we can see the formula for del. Del is actually 1 minus sum of individual loop gains plus sum of gain products of all possible combination of two non-touching loops minus sum of gain products of all possible combination of three non-touching loops, plus like that it goes on. So here the formula tells you that we need to find out the sum of individual loops, then the two non-touching combination, then three non-touching, then four non-touching, like that it goes on, and it based upon the problem given to us, based upon the graph, signal flow graph which we have. So in some graph where we can get even four non-touching, five non-touching loops also, combination also. But in some problem where we will be getting only two non-touching, in some other problem where we will not get even two non-touching also. That depends purely on the signal flow graph given to us. So therefore, the formula tells you that it is the formula here is to find out the transfer function C of S by R of S. Formula is 1 by del summation of pk into del k, where del, as we already discussed, it is 1 minus sum of individual loop gains plus sum of two non-touching plus sum of minus sum of three non-touching plus sum of four non-touching, like that it goes on. So the next sign, the polarity will be changing alternatively for the terms. For example, here you can see that the second term is negative term, where the next adjacent term will be having positive. Then the next term will be having negative term. Like that it goes on. The sign will be alternatively changing. Then we should find out the del k. Here the del k is actually the del for the part of graph which is not touching that kth forward path. So as we know that we have to find out the number of forward paths. So for each and every forward path, we have to find out which is the part of graph that is not touching that forward path. So for that part of graph, we have to find out the del. So our work is here to find out what is the part of graph that is not touching that kth forward path, right? Then that part of graph has to be segregated, and then for that part of the graph we have to find out the del value. So that is actually the del k. So I think we can go for a problem so that we can understand better. So here I've taken a problem. So this is the signal flow graph given. So here we can see that it is having nodes from 1 to 6. So it is moving from 1 to 2 with gain G1. So for each and every path, the gain is denoted here. So 1, 2, 3, from 2 to 3, from 3 to 4, 4 to 5, 5 to 6. So this is the signal flow graph given. So now the first step of doing signal flow in order to get the transfer function is we need to find out what is k. K is nothing but number of forward paths. So let us identify the forward path. So here you can see that the first forward path will be from 1 to node 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Yeah, so therefore let me take this as my first forward path, which is from node 1 to 6. So that is what here redrawn here, 1 to 2, 2, 3, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Let me take this as my first forward path. And for this forward path, we have to find out the gain. That is actually the P1. It is written here. You can see the first forward path gain is P1, because here, in order to get the gain, what we have to do is we have to get the product of all the gains in that particular forward path, right? So in this forward path, if you see, the gains are G1, G2, G3, G4, and G5. Right. So therefore, in order to get the gain of that forward path, we have to get the product of all the gains here. So therefore, G1, G2, G3, G4, G5 will be the gain of the first forward path. Similarly, we have to find out, we have to check, do we have any other forward path? So here in this problem, if you check here, you can see that from node 1 to 2, 2 to 3, then from 3 to 4, there is a direct jump from 3 to 4, from 5 to, then from 5, there's a path going for 6, right, to the node 6. So that is what we're going to take it as second forward path. So here you can see the second forward path is from 1 to 2, 2 to 3, then from 3 to directly it is jumping to 5, and 5 to 6. So this is another forward path. We can find it in the signal flow graph. So let me take this as my second forward path. Again, for the second forward path, I have to find out the gain. So for each and every forward path, we have to find out the gain. So here for the second forward path, the gain will be again product of all the gains in that particular forward path. So therefore, here the gains are G1, G2, G6 into G5, because here you can see 1 to 2, the gain is G1. From node 2 to node 3, there is a gain of G2. Then from 3 to node 5, there is a gain of G6. Then from 5 to 6, the gain of G5. So what I have to do? I have to get product of all the gains. So therefore, my P2, that is a gain of the path, second forward path P2 will be G1, G2, G6, G5. Right. So first step is we need to find out the forward path, possibilities of forward path, and for each forward path we have to find out the gain. Then the second step is we have to find out the total. We have to find out the possible individual loops available in the signal flow graph. So again, go back to the graph and check whether how many loops individual loops you can find out here. That is single loops you can find out here. So from the graph, by observing the graph, we can find out the loop 2 to 3, right? This loop. Let me take this as my loop 1, because you can see that loop is a one where we know that if it starts from a particular node, it should end up at the same node without crossing any node more than once. That is actually the definition of loop, right? So therefore, we can get a loop where it is starting from node 2, it is moving to node 3, again back to node 2. So therefore, this is actually a loop, right? So I can take this as my first loop. Similarly, the second loop will be from 3 to 4, again from 4 to back again to 3. This is actually the second loop. Then we have one more loop from 4 to 5. From 4 to 5, then again from 5 to back to 4. So this is actually the third loop. So loop 1, loop 2, loop 3. And apart from these 3 loops, we also have one more loop, that is from node 3 to 5, then from 5 to 4, then from 4 to 3. Is that clear? So the fourth loop is again from 3 to 5, then from 5 to 4, then from 4 to 3. So this is actually the fourth loop. So therefore, here you can see that the possible single loops available in that signal flow graph. So here you can see this is actually loop 1 from 2 to 3, then from loop 2, 3 to 4, then loop 3 from 4 to 5, and the fourth loop is from 3 to 5, then from 5 to 4, then from 4 to 3. Right. So these are the loops, right? Individual loops available in the signal flow graph. So again, for these individual loops, we have to find out the gain. For each and every loop, we have to find out the gain. So again, for getting gain, what we have to do, we have to product all the gains in that particular loop, right? So for the first loop, if you take P11, right? P11 is the first loop gain, and the first loop gain will be G2 into H1. Forward path gain is G2, and the feedback gain is H1. So therefore, to get the gain of this particular loop, I have to get the product of G2 and H1. Similarly, you find out the loop gain of second loop. That is, for second loop, the gain will be G3 into H2. Just get the product of gains in that particular forward path as well as in the feedback path. Likewise, we have to get the gains of individual loops. So therefore, here we can see that for the first loop, the gain is G2H1. For the second loop, it is G3H2. For the third loop, it is G4H3. And for the fourth loop, you can see that the gain will be G6 into H3 into H2, right? So from 3 to 5, the gain is G6. From 5 to 4, it is H3. Then from 4 to 3, it is H2. So multiplying all the gains will be giving you fourth loop gain will be G6 into H2 into H3. So like this, we have to get the gains of individual loop. Then the next step would be, right, then the next step is we have to find out how many number of two non-touching combinations are available. Just go back to the loops and just check whether you have any two non-touching loops available. Right. So if you check here, if you check with the, if you take the first loop and if you're going to check with the other three loops, if you're going to check with the second loop here, we can see that the node 3 is common in both loop 1 as well as in the loop 2, which means that they both will be touching each other, right? If you say the loops are not touching, which means that it should not have any common node, right? So therefore, if I'm going to check the loop 1 with loop 2, here we can see that it is having common node as 3. So therefore, they will be touching. Similarly, if you check with the loop 1 and loop 3, here we don't have any common node. So therefore, damn sure we can say they are not touching. So therefore, the loop 1 and loop 3 are not touching. So therefore, we got one combination of two non-touching loops. Again, if you check with the fourth loop, again, there's a common node 3 available. So they will be touching each other. So comparing all the four loops, you can see that the loop 1 and loop 3 are not touching. So we get one combination of two non-touching loops. Right. So there is only one non-touching loop, that is loop 1 and loop 3. So again, to get the gain of this two non-touching combination, we have to multiply all, we have to get the product of all the gains here. So when you get the product of all the gains, G2 into G4 into H1 into H3. So that is actually the gain of the two non-touching combination, right? So only one two non-touching combination is available. And for that one two non-touching combination, the gain will be the product of all the gains, G2, G4, H1, H3. So that is actually the gain. And if you go on again, you have to compare whether you have any other combination of two non-touching. But here, if we see that there's no other combination of two non-touching available, and three non-touching also is not available, four non-touching not available. So likewise, you have to check it for all the combinations. Then after finding two non-touching, now we have to find out the del part. When you take the del part, as we know the formula already, del is equals to 1 minus sum of individual loops. So here we have totally 4 loops, right? So P11, P21, P31, P41. So just sum up all the loop gains, individual loop gains, plus sum of two non-touching. Here we have only one combination of two non-touching, that is actually P21. Yeah. So just substitute in the formula where you will be getting your del value. Now comes the next important part, which is our del k part, right? Del k part, where del k part is nothing but k is nothing but number of forward paths. For this problem, we have totally two number of forward paths. Let me take the first forward path. Let me go back to the first forward path. So in this, taking the first forward path, we have to compare with the original graph, and we have to check whether any part of graph is not touching this first forward path. So if you check here, you can see that there is no part of graph which is not touching the first forward path at all. If you find any part of graph which is not touching the first forward path, then you have to take that part of graph, and for that part of graph, you have to find out the del value, right? But here you can see by checking, you can see that there is no part of graph which is not touching the first forward path. So therefore, my del 1 value will be 1, because here you can see del 1 value will be 1 because there is no part of graph that is not touching the first forward path. Similarly, you have to go and check the second forward path, and if you check the second forward path with the original graph, only node 4 is not touching. But if you see at the node 4, there is no complete part of graph, right? If you get a complete part of graph, then for that complete part of graph, you have to find out the del value again. But here again, we don't have any complete graph, complete part of graph which is not touching the second forward path. So therefore, for second forward path also, the del value will be 1. Yeah, so that's why we are getting del 1 1 and del 2 also 1. After finding all these things, we have to substitute everything in the formula in order to get the transfer function. So you know that the transfer function is 1 by del summation of k pk into del k. So when we expand this formula, it is p1 del 1 plus p2 del 2 by del, because here the number of forward paths is 2. So therefore p1 del 1 plus p2 del 2 divided by del. So as we already found p1 p2, right? As we already found p1 p2, del 1 del 2 value are 1, and del value also we found. So substituting everything, we will be getting the transfer function of the given signal flow graph, right? So this is how we have to get the transfer function from the given signal flow graph, right? So first thing we have to get, we have to find out the number of forward path and for gains of that forward path. Then we have to identify the individual loops, then 2 non-touching, 3 non-touching, 4 non-touching, it depends upon the problem. Then we have to get the del value, and then we have to get the del value for each and every part of the graph which is not touching those forward paths. Then finally, we have to substitute everything in order to get the transfer function. So this is how we have to get the transfer function from the signal flow graph. Thank you.